All right, so real quick here, what I'd like you to do, while I'm taking a roll, I want to set you up to do something. All right, so the next step for us is going to be it's not much of a step. So this looks a lot like the problems we've been doing, right? It's asking you to find all the zeros of a polynomial, but there's one word that's different. Complex. Complex is the word that's different. Okay, so in the past, all the work that you've done.
Please excuse that sixth period art students arrived back a little late from their field trip. That's the sixth period art students from Mrs. Rush arrived a little late from their field trip.
Okay, so all the work we've done in chapter or module 6 and in module 7 with polynomials, whenever we've looked for zeros or solutions to equations, we've only looked for real zeros or real solutions, right? So let's remind ourselves, it's been a while since we talked at all about complex numbers, what it means to be a complex number. What is that? Okay, it could have i's in it, right? So the set of complex numbers is the set of all possible numbers. A subset of that is the set of real numbers, right? So we've got this, if we want to like draw a Venn diagram, we've got the set of complex numbers, and then inside of that, we've got the set of real numbers, of pure real numbers, and then we've also got the set of pure imaginary numbers. Right? Yeah, that's fine. Yeah. So then the complex numbers are all the numbers that we could write in the form a plus b times I, right? Where I is the imaginary unit, that's square root of -1. So the real numbers, the set of pure real numbers, those are going to be, that's the set where b is equal to 0, right? Where there is no imaginary part. Every number you ever dealt with prior to this year in module 3, when we finally were introduced to imaginary numbers, every number you'd ever dealt with was contained in this set, this subset of real numbers, right? This set of pure imaginary numbers is going to be the set where there's no real part, where it's just, all it has is some number times I. And that's going to be where a is equal to 0. But there's a whole bunch of other numbers here that have both real parts and imaginary parts, and those would be all the rest of the complex numbers. But all of these are complex numbers, right? So complex numbers would include real zeros, and it would also include zeros that have i's in them, right? So we're expanding our search a little bit, okay? So how does that change things? Well, not very much, really. It's just, all it's going to do is it's going to add some extra answers that we didn't get before, that we never looked for, right? Like, for example, when you do this problem here, how are you going to approach this one, right? If we're trying to find the zeros of this polynomial, what's our strategy? What are we going to do? We always are trying, when we're trying to find zeros of polynomials, we're always trying to factor the polynomials and then use the zero product property. Set the factors equal to 0 to find the individual zeros, right? That's always our goal. So here we've got a cubic polynomial, so we got to break this thing apart. But what's our strategy for factoring it? Well, okay, magic numbers, no. Magic numbers would be what we would do if it were quadratic, right? If it's quadratic, if we have 3 terms, then then we're going to use our strategies for quadratic stuff, right? But that doesn't have 3 terms. How many terms does it have? 2. It's the number of terms that determines the strategy, right? 3 terms, it's a quadratic trinomial. 4 terms, what do we do? We've had a lot of practice with that. Split it in half and group it. What do we do with 2?
Find
the factoring pattern. So we got to find the factoring pattern, right? So what's the pattern that's going to go with this one? Right, that's going to be a difference of cubes. Everybody agree? Because I've got an x cubed and I've got minus something. So we know it's going to be a difference of cubes is what we're looking for. So the question is then, could we write this as something cubed minus something cubed, right? So let me scoop those down just a little bit. Could we do that? 125 is what cubed? Okay, what about the 64x cubed? What quantity is that cubed? 4x. Everybody see that? Okay, if we can see that stuff, then we're home free. Now all we have to do from here is just follow the pattern, right? So that's an a cubed minus b cubed pattern. Not everybody knows these completely, so I'm going to force you to know them. Here's how I'm going to force you to know them. I'm going to force you to know them because you're going to have a quiz over them. Okay, if you go to the Unit 3 practices or the resources, if you go down, remember the part where we multiplied polynomials was in 6.2. So if I go to the 6.2 resources, there's a product patterns handout. It's going to be over that stuff, right? Knowing those patterns, because those are really useful to know. And they show up on these tests. And then also, if we go down to 6.4, which was the factoring section, I added something. In 6.4, the factoring patterns handout. Look at this. This is good. Right? So that's a reminder of the 4 factoring patterns that we know. Right? So you got to have those memorized. This is going to be, and I'm going to give you an opportunity here, because we haven't done this yet. We're going to do our memorization quiz, right? Well, this stuff's going to be on it too. It's going to be factoring patterns, product patterns, and then perfect squares and perfect cubes. And then you get a chance to get an Algebra 2 test grade for just memorizing some stuff, right? Pretty easy. All right, but in the meantime, I'll put that on the calendar. So remind me real quick, what is the difference of cubes pattern? What's the difference of cubes pattern? Remember? Okay, good. So whatever the sign is between the cubes, that's the sign that goes between the A and the B, right? What's the rest of it? Valerie, you remember the rest of it? So we get A minus B, then what?
A2.
Okay, A squared plus, good.
AB.
AB, excellent.
And minus
No, plus. The last one's always plus. Plus
B.
B squared. Good. There we go. Okay. So all we have to do is just match that stuff to RA and RB, right? Does that make sense? And so this looks really familiar. We've done a lot of stuff like this, right? So the first one is going to be what?
4x
Minus 5, because A was 4x and B was 5, right? So we get 4x minus 5. Now here's the tricky part. Brandon, what is A squared going to look like? What's A? Okay, good. A is 4x. Good. So you saw the trick. So A is 4x, and if we square that, that's going to actually give us a 16x squared, isn't it? Right? And then plus, see, we can just draw a correlation here with each of these. What's A times B going to be? Bailey? Okay, now the B is just the 5, right? And the A is just the 4x. So here we've got a plus A times B, so this is actually going to be a positive 20x. Does that make sense? And then what about B squared? What's that going to be? 25, good. Okay, so then here's our new polynomial, right? We took this one up here,
Nicole,
and we traded it in
come
for
to the
this
office,
one.
please.
And this whole thing is equal to 0. So what we always said up till now, because this pattern, we end up with this irreducible quadratic, we never bothered looking for any zeros of that, right? It's because it's not going to give us any real zeros. It never does, right? So we always just crossed that one off and said, okay, well, we only get one real 0. When I set this guy equal to 0, what are the 2 steps to solve for x? Add 5 and divide by 4, what's that give us? 5 over 4, there we go. So there's the only solution we would have gotten before, but now we can go, well, we could always have gone further, but now we're going to go further, and we're going to find this other one as well. So that's what I want you guys to work on right now, is let's set this other factor equal to 0. And here's something I kind of want you to see. You've been working on this stuff. When we're trying to find zeros, remember that we can, as soon as we have this thing broken up enough that we can take care of the individual pieces, we can stop factoring, right? As soon as we get these things down to a quadratic factor, we can stop, because we could always just use the quadratic formula then, right? Sometimes it's convenient to keep factoring further if it's easy to do, but otherwise we won't. Like in this case, it's not going to factor, right? So we'll just take this quadratic factor and set it equal to 0, and then we just have to solve that little equation to get the other zeros, right? One of them came from this factor. Now you're going to try this one. Okay, so go. While I take roll, I want you to work on that. Got your notebooks out. See what you can do. See if you can come up with the answers for that. Okay? So how are we going to solve that? Because you kind of have to think about this. When you're doing these problems, you kind of have to compartmentalize your thinking. You're going to get it down to a certain stage, and then you're going to focus on that one sub-problem, right? So we got this big problem. We broke it up into smaller pieces, and now we're going to set each of those factors equal to 0 and solve. First one's done. Now we got to deal with this one. So this is really a module 3 problem. It's a quadratic equation. Those are always solvable. They're always pretty easy. I mean, sometimes there's some simplification to do, but worst case scenario, we put it in standard form and plug it in the quadratic formula, which is exactly what we're going to do, right? So what's A, B, and C here? 16, 20, and 25. Good. Okay, so this is A, right, and then we got B and C. And so we're just going to plug that stuff into the quadratic formula and see what we end up getting, right? So x equals, real quick everybody, without looking, tell me the quadratic formula. Think about it in your head for a second. What is it? You all should know. Remember the song. Okay, so what is it? Okay, you're on. Hang on. X equals negative b plus or minus. You got it? And what's inside the square root? Remember that one, right? Divided by 2. You remember that. We'll have to listen to that again.
No, we don't.
Oh, okay, we don't have to. You got it? Okay. So let's plug that stuff in. All we got to do, x equals negative b, so that's negative 20 plus or minus the square root. What's 20 squared? 400, right? 2 squared is 4, and I got 2 zeros, right? So 400 minus 4 times 16 times 25. All divided by 2 times A, what's that? What's 2 times 16? 32. Okay, so that's all we got to do is just simplify that big ugly expression right there. Well, we can do that. So first of all, let's maybe figure out what this number is. What's a convenient way to multiply those 3 numbers together? 4 times 16 times 25. And this stuff is important. You got more and more. I can see you getting a lot better at this kind of thing. Any suggestions? Alexis, how would you multiply 4 times 16 times 25? In what order? What do you think? Is there a way that just jumps out at you as being an easy way to do it? Because you got to do it in pairs. So see if you can pick an easy pair first. What is it going to be? 4 times 25 is what? 100. And 100 is an easy thing to multiply by. You just add 2 zeros, right? So that's going to give us 4 times 25 is 100 times 16 is what? 1600. Yeah. So we end up with 4, and then inside it's pretty easy. We get 400 minus 1600 is how many hundred? Negative 1200, right? So this whole thing becomes negative 20 plus or minus the square root of negative 1200, all divided by 32. Okay, what's the negative inside the radical going to do, sir? Okay, that's going to give us an I, isn't it? So right away we know that negative is going to come out as an I. And then we want to think of a big perfect square that goes into 1200. Well, that's a huge number. But there's one that's going to be a pretty easy one that we've already kind of seen up here. What's a big perfect square of 1200? 16 is 1, you're right. We can get bigger. What is it? 400. We could have done maybe 100 and just done it in 2 steps, but remember, we already had 20 squared equals 400 up there, didn't we? Right? So we could break this one down. We could break this down into negative 32 plus or minus. The square root of 1200 is going to be the square root of 400 times square root of what? Yeah, we're going to get an I, aren't we? For sure we're going to get an I from the negative. But 3, isn't it? 400 times 3 is 1200. Agreed? Okay, and then here's the other thing we're going to do. While we're at this, to make things a little bit simpler, we know that our final answer, we want to be able to write it as a complex number in standard form. So we want to write it as, remember what those look like. We want to write it as a real part plus an imaginary part times I. So that means we're going to split this into separate fractions, right? So we're going to split the 32 and put the 32, well, that's supposed to be a 20, not a 32. So we're going to split the 32 up into each part of the fraction, which is okay to do because it's a common denominator. We can always split it into separate fractions, right? What's the square root of 400? You already told me? No, square root of 400?
Oh.
20. There it was. Okay, so now we can reduce this thing, can't we? What are we going to get for negative 20 over 32? What's that reduced to? Let's see, what's the number that goes into 20 and 32? Nah, 12 doesn't go to 20. Or 32. But what's one that does? 2 does, 4 does. 4 does also. 4 is a little bigger. So that's going to be negative, what? 8. Okay. Plus or minus, well, there's another 20 over 32, so that's going to reduce to 5 over 8. So we're going to get 5 times the square root of 3 over 8 times I. Okay. How many? Yes, ma'am. Yeah, go ahead. So how many solutions are represented there? How many zeros?
2.
2. How come?
Because there's, I got the negative 2.
Okay, I've got plus or minus, right? When we say or in math, it means 2 different things, right? So we've got the plus version and the minus version. So if I wanted to write these all down, Moodle wants you to write all of the complex zeros. So what would they be? Let's make a list. So we had 5/4, right? So our list would have been 5/4, comma, and then we would have had negative, was it 5/8?
Yeah.
Plus 5 times the square root of 3 over 8i, and then we would have put a comma, so we got to put a comma between each one. We would have had negative 5/8 minus 5 times the square root of 3 over 8 times I. So we would have had those 3 in any order, right? Now I want to draw your attention to something that happened here, something that's really going to be helpful. This is called the fundamental theorem of algebra. It's in the reading. I've got the resources are already there for 7.2, so you can look at it. But I'll just tell you what it is. It's really easy. What the fundamental theorem of algebra says is that the degree of a polynomial is linked to the number of complex solutions or complex zeros. So what's the degree of this polynomial that we started with? 3. You think it's an accident that we got exactly 3 complex zeros?
No.
It's not. In fact, it's always going to be that way. That's what the fundamental theorem of algebra says. The degree of a polynomial determines exactly the number of complex solutions you're going to get. Now, they may not be real. Some of them might be real, some of them might not, but you're going to get a total of 3 complex zeros. Now, I want you to notice something else that happened. Notice it down here at the bottom that 2 of our solutions came together, right? 2 of them had i's in them, and they came as the plus or minus part of what we call a complex conjugate. What does it mean to be a conjugate pair? We talked about this a while ago, but it's been a little while. A conjugate pair is just anything that fits this pattern. A conjugate pair would be where one term is, or one factor is a plus b, and the other one is a minus b, right? Where the two terms are the same, but the sign connecting them is one is plus and one is minus, right? And so if we look at our answers down here, we get complex conjugates because we get negative 5/8 plus some number times I, and we get negative 5/8 minus some number times I, right? So if conjugates are complex, the only difference is that there's going to be an I attached to the second term, right? And those just look like two complex numbers, but they always go together that way. Complex zeros always come in complex conjugate pairs, right? So the ones that have I's in them have to come in complex conjugate pairs. So let me ask you a question then. If we had a fourth degree polynomial, how many total complex zeros would there be? There'd be a total of 4, wouldn't there, right? So how many of those zeros, put that away please. How many of those zeros could be real? Guys, let's put phones completely away. I still want to, if they're out, they're just a distraction. Just put them away. How many total complex zeros are there going to be? Total of 4, right? Could you have, would it be reasonable to have all 4 of them be real?
No.
You could, and we've had that, right? We've had that happen before where we've had a quartic polynomial that had 4 real solutions, right? 4 real zeros. That's possible. What about, could you have 3 real?
No, yes.
You can't. You can't have 3 real, and here's why. Because the complex ones that have I's have to come in pairs. So you could never have a single zero that has an I in it. They have to always come in pairs of 2. And so if you've got one of them, you're guaranteed to have 2. So you could never possibly have 3 real solutions to a degree 4 polynomial. You'd either have to have 4 reals. What's the next lowest number you could have? 2. Because you got to save 2 then for the 2 imaginary ones. Could you have 1?
No.
Couldn't. Couldn't have 1, but you could have 0 and have 4 imaginary, right? So you might be asking, well, what about something like this? Because real zeros correspond to x-intercepts, right? So what about something like this then? What if we've got, here's my xy plane, and let's say here's my function. That could be a cubic function, couldn't it? Right, it's odd. Everybody agree? Okay, that's a cubic function. How many x-intercepts does it have? It's got 2. That doesn't seem to work though, does it? So that seems to say there were 2 real zeros. This one right here though counts as 2. Here's why. What happens when we have an x-intercept that bounces like that? Let's just say, for example, that this one occurs at x equals 5 and this one occurs at -2. What are the factors that go with those? X plus 2 and x minus 5, right? So if we were to write down our polynomial, it would look like x plus 2 times x minus 5. It's normal odd behavior, so we're not multiplying by -1, right? But what else do I have to do? I'm missing something. Ah, good. I've got to square this guy, right? Because it's bouncing. So that actually counts as 2 zeros. That's because it's bouncing and because it's being squared, we would say that x equals 5 has a multiplicity of 2 because it's being squared. And so if you take into account the multiplicities of factors, then they still always have to add up to the degree of the polynomial. Okay? That's pretty handy in math because that really allows you to predict how many you're going to get of each kind, and it's very, very helpful. It'll start to be helpful to you on these next couple of assignments you're going to do. Okay, let's try one more of these guys. How about something like that? We want to find all the complex zeros of that polynomial. How many complex zeros, Dalton, is that one going to have, guaranteed? What's that? How come? what determines how many complex zeros we have? Okay, all right, so you must not have been plugged in, 'cause we just talked about this. Somebody help them out. What's it gonna be?
The degree.
The degree. So what is that, Cyrus?
3.
3. The degree of the polynomial is the highest power of x, and that's 3, right? So we should have, we know we're gonna get 3 complex zeros. We don't know what they're gonna look like. Could it be that we're gonna get 0 real solutions? Okay. It's impossible, isn't it? It's impossible because the imaginary ones have to come in pairs. So the most we could get, if we only get a total of 3, the biggest number of imaginary ones would be 2, right? So that means that we're going to get at least 1 real. That tells us, what's that tell us about the number of x-intercepts then? Is it possible to draw a cubic function without having at least 1 x-intercept?
No.
It's not. We have to have at least 1 real 0, and real zeros are x-intercepts, right? That makes sense though, doesn't it? If we think about what these things look like, right? Because what's the end behavior of an odd function look like?
Up in one direction, down.
Up in one, down in the other, right? So if it's a normal odd function, it could do this, but eventually it's got to go up. If it's down at this end, it's got to go up at this end. So somewhere it's got to cross the x-axis at least once. Agreed? Okay? So that kind of is consistent with what we're seeing. All right, so let's find these things then. What's our strategy going to be? And we got to think strategies here. If we're trying to find the zeros of this function, so we'll set it equal to 0, we got to factor it, right? That's always our goal, is to factor it. What's our strategy for 4 terms?
Split.
Split it and group it, right? Split it and group it. Okay, so we could split it right there and try to group it. Is it going to work?
Yeah.
Can anybody tell me why it's not going to work? You're right, it's not. It's hard to maybe see this at first, and it's never wrong to try it. If you don't get this, it's fine. You can just try it, and it's not going to work, but you can save yourself some time here. In order for grouping to work, what I always look for is the first term divided by the second has to give me the same result as this third divided by the fourth. Just look at the numbers. If the numbers don't work out, then it has no chance. 4 divided by 13, is that the same thing as 16 divided by 12? No, not even close. So it can't work, right? It can't work. We could try it, but it's not going to. Just trust me. So now what? What's our strategy if it doesn't factor? Well, we can't. Okay, why can't we do that? That's usually a good idea, right? What are you thinking quadratic form? What are you thinking on that? You thinking difference of squares or difference of? Okay, that's a 2-term pattern, right? We got 4 terms here, so none of those factoring patterns are going to work with 4 terms. They only work with 2. Right? So we can't factor it though. We already tried. The only strategy we've got to factor it directly is grouping, and it didn't work. What did we just learn though? If we've got a polynomial that has integer coefficients, right, then we can always find a list of zeros that we could try to see if they work, right? How do we generate that list?
Isn't it the first one you lost?
Yeah, good. It has to do with the leading coefficient and the constant, right? Right. We're going to look for factors where the numerator is the top of the fraction is a factor of what? The constant, right? So we're going to get factors of 12 divided by factors of 4. Well, what are the factors of 4? What could we get in the denominator? We could either get a 1 or a 2 or a 4. What's the easiest one to deal with? 1, for sure. If a 1's in the bottom, then it's an integer. It's not, the fractions becomes an integer, which is easy, right? So those are the ones we'll always try first. So if we're dividing by 1, then it's just going to be the factors of the constant, right? So let's make our list. What are those going to be? So x equal, what are the factors of 12?
1.
So plus or minus 1. So 1 minus 1, 2 minus 2, 3 minus 3, 4 minus 4, 6 minus 6, 12 and minus 12. And then finally, if we go through that whole list and we don't get a hit, then we could move on and try the factors of 12 divided by 2, right? And so that would give us, if I divide all these by 2, the first ones I'm going to get are 1/2 minus 1/2. 2 divided by 2, that's just, we already did that, that's 1. But we could get 3 divided by 2, negative 3/2, etc. But we're never going to get there, right? That's pretty far down the list. If it gets that far, that's a lot of work. Yeah, I wouldn't blame you. So you're never going to have to go that far, right? So we're just going to try these out. Now let's remind ourselves how we do that, right? This is that whole thing where we're going to set up that synthetic division kind of a table, so we can do it really quickly, try a whole bunch of numbers, right? So how do we do that? What do we put at the very top? Coefficients. So we got 4, 13, 16, 12, and then remember we're going to make a column under the last digit, and that's going to be the remainder column, right? That takes the place of the remainder box. Okay, and then we're just, each row corresponds to a test value. We're going to try them out. So what about 1? What do I do first? Drop down the 4. Because remember, what we're putting in this row, those are the numbers that would be the ones below the bar in synthetic division. So we drop the 4 all the way down. Good. Now how do I get the next one? So I got to multiply and then add, right? So 4 times 1 is plus 13. Okay, what do you think's going to happen here? Well, yeah, why is this not going to work? It's never really going to.
Bigger than 12.
And notice that if all these numbers up here are positive, and this number is positive, every time I multiply and add, I'm just getting a bigger result, aren't I?
Yeah.
So it's never going to work. That's never going to get down to 0. It's only going to get bigger, right? So should I even try any positive numbers? No, they're not going to work, are they? Positive integers aren't going to work. Okay, so let's just, 1 didn't work. We'll skip -1 and we'll go on down to 2. Let's try 2. If I bring the 4 down, now what? 2 times 4 is 8 plus, oh, we want negative, sorry. What am I doing? I said not to do that. We want to do the negatives. Okay, so let's try -1. So we bring down the 4, right? Bring the 4 straight down. -4 plus 13 is -9 plus 16 is, was it 7? So it's not going to work, is it? Okay, so -1 we can cross off the list. Let's try -2. Bring down the 4. -2 times 4, -8 plus 13, 5, good. -2 times 5 is what? -10 plus 6, -2 times 6, -12 plus 12. So that was a winner, right? We got that one to work. So -2 was a hit. Now look what we're left with. What we're left with now, we got 3 terms, right? So this is the coefficient of what, or what is that? Constant? Coefficient of, okay, so that's quadratic, right? So what we're left behind when we divide through the -2, now we're dealing with a smaller polynomial whose zeros we need to find. So let's look at this one. So this is 4x squared plus 5x plus 6. We want to find the zeros of that. So let's see. What are our options for solving this? Somebody throw out an option. Magic numbers, meaning in this case it'd be bottoms up, right? So could we find numbers that multiply to a times c, that multiply to 24 and add to 5? Multiply to 24 and add to 5? No way, right? That's not going to work. The smallest numbers we could use would be 4 and 6, and they add 10. So it's not going to factor, is it? We shouldn't even try. So what's our other option? Quadratic formula. Now, what are the values of a, b, and c? Good. A is 4, B is 5, and C is 6, right? I mean, they just come right out of our table. So now we can just plug those into the quadratic formula and see what we get. So x would equal -b plus or minus the square root of b squared, 25, right? Minus 4 times a times c, which is 6, right? All divided by 2 times 4 is 8. So let's look inside the radical and see if we can figure out what that number is. So inside the radical, how can I multiply those together easily? 6 times 4 is 24, times 4, and multiplying by 4 is doing what again? Doubling twice. So 24 doubled is 48, and then 48 doubled is 96. So in here we end up with 25 minus 96. What's that? How do I subtract two numbers, one big and one small? Remember the trick for this, going way back to grade school? I'm sure you learned this. You can always just subtract the little one from the big one, but keep the sign of the big one, right? So 96 minus 25 is what? 71. But it's going to be negative, isn't it? So this is going to become, everything in here is going to become a negative 71, right? So then what this problem looks like, let's see, then we end up with negative 5 plus or minus the square root of negative 71 all over 8, right? So what's the negative do? Comes an I outside. And are we going to be able to find any perfect square factors of 71? No way. There aren't any. So then our answers are pretty much done. We'll pull this apart into two fractions, right? So we get the negative 5 over 8 plus or minus goes in the middle.
Curtis, come to the office, please. Kyle Curtis, come to the office.
Square root of 71 over 8 times I. How many solutions are there? 2. One of them is negative 5/8 plus the square root of 71 over 8 times I. And the other one is minus, right? So we got all 3. There's those 2, and what was our other one? Negative 2, right? So there's 3 total, which makes sense, right? Because it was a degree 3 polynomial, so we knew it had to have 3 total, right? Make sense? Okay, you got an assignment. Jump to it.
Okay, I'm going.